The cosmos is a vast, silent expanse, defined not merely by the luminous stars that puncture the darkness, but by the intricate, invisible gravitational tapestry that weaves celestial bodies together. When we look up at the night sky, we are often drawn to the static nature of the constellations, the fixed points of light that have guided navigation and storytelling for millennia. However, the reality of our solar system is one of constant, dynamic motion. It is a complex mechanical clockwork where every object, from the massive gas giants to the microscopic grains of cosmic dust, is engaged in a perpetual orbital dance. Within this grand choreography, the Earth is not merely a solitary traveler accompanied by a single, pale satellite. It is the gravitational anchor for a variety of transient visitors, a bustling intersection of orbital pathways that occasionally traps wandering matter in a delicate embrace. We gather here to discuss a specific, recent addition to this catalog of celestial companions. The National Aeronautics and Space Administration, known globally as NASA, has formally confirmed the presence of a new object within our immediate cosmic vicinity. This object is designated as 2025 PN7. It is not a moon in the traditional sense. It does not possess the mass, the permanence, or the circular stability of the lunar body we see every night. Instead, 2025 PN7 is classified as a quasi-moon, a tiny asteroid that has fallen into a specific resonance with our planet. It is moving in step with Earth, a synchronized swimmer in the immense pool of the solar system, and it is projected to remain in this configuration until the 2080s. To understand 2025 PN7 is to understand the subtle nuances of orbital mechanics, the history of planetary formation, and the dynamic, evolving nature of the space environment that Earth inhabits. Our exploration begins with the fundamental nature of the Earth-Moon system and how our understanding of satellites has evolved. For the vast majority of human history, the Moon was a singular entity. It was the Moon. It was the only object of significant size orbiting our planet. However, as our observational technology has transitioned from the naked eye to ground-based glass lenses, and eventually to sophisticated space-based observatories and radar arrays, we have realized that the gravitational influence of Earth extends far beyond the Roche limit of our primary satellite. We inhabit a gravity well that interacts with the Sun's gravity well, creating regions of stability and instability. It is in these regions that objects like 2025 PN7 are found. The discovery of an object like 2025 PN7 is a testament to the staggering precision of modern astrometry. The designation itself, 2025 PN7, reveals the time frame and sequence of its identification. In the nomenclature of the International Astronomical Union, the year indicates the discovery period, while the alphanumeric code follows a strict sequence indicating the half-month of discovery and the order in which the object was catalogued. Finding such an object is an exercise in detecting the faintest of movements against a background of fixed stars. These quasi-moons are often no larger than a city block, sometimes as small as a school bus, and they are composed of rock with low albedo, meaning they reflect very little sunlight. They are dark, carbonaceous or siliceous fragments drifting through the void, rendering them nearly invisible to all but the most sensitive wide-field survey telescopes. The detection of 2025 PN7 likely utilized the technique of blinking, a process where multiple images of the same patch of sky are taken over a period of time. By layering these images, astronomers can subtract the static background stars, Anything that remains, anything that shifts position relative to that background, is flagged as a potential solar system object. Once a candidate is identified, a global network of observatories is alerted. They turn their instruments toward the coordinates to verify the sighting, and crucially, to track its motion over days and weeks. It is this tracking that allows mathematicians and astrophysicists to calculate the orbital elements, the eccentricity, the inclination, the semi-major axis, and the period of the object. In the case of 2025 PN7, the calculated orbit revealed something fascinating. It was not simply passing by Earth on a hyperbolic trajectory, destined to fly off into the outer solar system, never to return. Nor was it on a simple elliptical orbit around the Sun completely independent of Earth. Instead, its orbital period, the time it takes to complete one revolution around the Sun, was almost exactly equal to Earth's orbital period of 365.25 days. This is what astronomers call a one-mean motion resonance. When two celestial bodies share an orbital period, their gravitational interaction becomes cumulative. They push and pull on each other in a rhythmic, periodic fashion. However, calling 2025 PN7 a moon is a simplification that requires scientific correction. A true moon lies deep within the planet's Hill sphere, the region where the planet's gravity dominates over the Sun's gravity. A true moon orbits the planet in a path that, if viewed from above, looks like an ellipse or a circle with the planet at the center. 2025 PN7 behaves differently. It orbits the Sun just as Earth does. However, because it shares our orbital period, it stays in our vicinity. If you were to map the trajectory of 2025 PN7 from a reference frame fixed to the Sun, it would look like a standard ellipse. But if you change your perspective and map its trajectory from a reference frame fixed to the Earth, the pattern changes dramatically. From our point of view, the asteroid appears to trace a complex, kidney bean-shaped or horseshoe-shaped path around our planet. This horseshoe orbit is a hallmark of co-orbital objects. As 2025 PN7 orbits the Sun, it may drift slightly ahead of Earth. When it does, Earth's gravity tugs it backward. Paradoxically, in orbital mechanics, losing energy or being pulled back causes an object to drop to a lower orbit, which actually speeds it up. Conversely, if it falls behind, Earth pulls it forward, adding energy, which raises its orbit and slows it down. This counterintuitive dance keeps the asteroid trapped in a loop relative to Earth, drifting toward us and then away, but never colliding and never fully escaping. At least, not for a while. The confirmation that 2025 PN7 is in this specific configuration is what grants it the title of Quasi-Moon. It effectively functions as a satellite, appearing to orbit us, even though the Sun remains its primary gravitational master. The specific duration of this relationship, extending until the 2080s, highlights the transient nature of these bodies. Unlike the Moon, which has been our companion for billions of years and will likely remain so until the Sun expands into a red giant, quasi-moons are temporary visitors. The orbital resonance is metastable. It is a balancing act that can be disrupted by the gravitational perturbations of other planets, particularly Jupiter and Venus, or even by the chaotic evolution of the asteroid's own orbit over decades. The prediction that 2025 PN7 will remain with us until the 2080s is derived from complex numerical simulations. Supercomputers take the current position and velocity of the asteroid, along with the positions and masses of all major solar system bodies, and run the clock forward. These n-body simulations integrate the equations of motion millions of steps into the future. They show that for the next several decades, the resonance holds, but eventually, the delicate balance will tip. The asteroid will likely drift too far, gain or lose too much energy, and transition into a different type of solar orbit, perhaps becoming a standard Apollo or Aten-class asteroid, leaving Earth's immediate company behind. Moving beyond the mechanics of its discovery and orbit, we must address the scientific importance of 2025 PN7. Why does the astronomical community react with such interest to a small rock that will only be with us for half a century? The answer lies in what these objects tell us about the composition and history of the inner solar system. Every asteroid is a time capsule. They are the leftover building blocks of planetary formation, the debris that failed to coalesce into a planet during the chaotic early days of the solar nebula 4.6 billion years ago. By studying them, we study our own origins. 2025 PN7 is particularly interesting because of its location. Being a co-orbital object, it is energetically very accessible. In terms of delta V, the change in velocity required for a spacecraft to reach an object, rendezvous with a quasi-moon, requires significantly less fuel than reaching the main asteroid belt between Mars and Jupiter. It is, in some scenarios, easier to reach than the surface of our own moon. This makes 2025 PN7 a prime target for scientific observation and potentially future sampling missions. There are prevailing theories regarding the origin of such quasi-moons that elevate their scientific status. Broadly, there are two main categories of origin for an object like 2025 PN7. The first theory suggests it is a captured asteroid. In this scenario, 2025 PN7 formed elsewhere in the solar system, perhaps in the main belt or even further out, and was perturbed by Jupiter's massive gravity. It spiraled inward, eventually crossing Earth's orbit at just the right speed and angle to get caught in the 1 resonance. If this is the case, 2025 PN7 is a sample of the distant solar system brought to our doorstep. It could be a carbonaceous chondrite, rich in organic compounds and water ice, offering clues to the delivery of water to the primordial Earth. The second, and perhaps more tantalizing theory, is that 2025 PN7 is a piece of the Moon itself. We know that the Moon has been bombarded by asteroids and comets for billions of years. The sheer number of craters on the lunar surface bears witness to this violent history. When a large impactor strikes the Moon, it ejects tons of material into space. Much of this material falls back to the lunar surface, and some escapes the Earth-Moon system entirely to orbit the Sun. However, computer models suggest that some of this lunar ejecta can become trapped in Earth-like orbits, evolving into quasi-moons. This hypothesis has been strengthened by observations of another quasi-moon, Quasi-Moon, which spectroscopic analysis suggests contains silicates similar to those found in lunar samples brought back by the Apollo missions. If 2025 PN7 shares this origin, it represents a piece of the Moon that we can study without landing on the lunar surface. It would effectively be a distinct geological province of the Moon, separated by time and space, floating freely for us to examine. Determining which of these theories is correct requires detailed spectral analysis. Spectrometry is the science of measuring the interaction between matter and electromagnetic radiation. As sunlight hits the surface of 2025 PN7, some wavelengths are absorbed and others are reflected. The pattern of reflected light, the absorption lines, acts as a chemical fingerprint. If the spectrum shows deep absorption bands around 1 and 2 microns, it would indicate the presence of pyroxene and olivine, minerals consistent with lunar origin or S-type stony asteroids. If the spectrum is flat and featureless with low reflectivity, it points toward a carbon-rich C-type asteroid. The size of 2025 PN7 is another critical variable. While the source description characterizes it as tiny, in astronomical terms, size dictates physics. A very small object, only a few meters across, is a monolith, a single spinning boulder held together by internal chemical bonds, van der Waals forces, and crystal lattices. A larger object, hundreds of meters across, is often a rubble pile, a loose aggregation of rocks and dust held together only by mutual self-gravity. Understanding the internal structure of 2025 PN7 helps us model how it rotates. The Yarkovsky-Kiev-Radzievsky-Paddock effect describes how sunlight can spin up an asteroid. Photons hitting the surface heat it up. As the asteroid rotates, the afternoon side radiates this heat away as thermal photons. This thermal radiation exerts a tiny, localized thrust. Over millions of years, this can spin an asteroid up until it breaks apart or slow it down until it tumbles chaotically. As a quasi-moon, 2025 PN7 is subject to these forces, and its rotational state can tell us about its density and age. We must now pivot to the broader implications of this discovery and what lies next for our understanding of Earth's neighborhood. The identification of 2025 PN7 reinforces the concept of a dynamic space neighborhood. We often think of space as empty, but the region around Earth is teeming with activity. There are thousands of near-Earth objects. Identifying them is the first step in the mandate of planetary defense. While 2025 PN7 is in a stable resonance and poses no threat of collision with Earth in the foreseeable future, studying its orbit refines our ability to map and predict the paths of other, potentially hazardous objects. The 2080's end date for its current orbital phase provides a tangible deadline for observation. We have a limited window of roughly 50 to 60 years where this object is easily accessible. This creates a compelling case for a robotic mission. A small satellite, perhaps a CubeSat-class mission, could be launched to rendezvous with 2025 PN7. Such a mission could perform close-range photogrammetry to map its topography, creating a 3D model of its shape. It could use an X-ray spectrometer to determine elemental abundance, how much iron, magnesium, silicon, or aluminum is present on the surface. Furthermore, the study of quasi-moons like 2025 PN7 has implications for in situ resource utilization, a cornerstone concept for the future of space exploration. If humanity is to become a multiplanetary species, we cannot lift all our supplies from the bottom of Earth's deep gravity well. We must learn to live off the land. Asteroids are potential fuel depots and construction yards. Some are rich in hydrated minerals that can be baked to release water. This water can be split by electrolysis into hydrogen and oxygen, rocket fuel and breathing air. Others are rich in metals like platinum, nickel, and cobalt. Because quasi-moons are dynamically close to Earth, they are technically the most energy-efficient sources of extraterrestrial material. 2025 PN7, therefore, is not just a scientific curiosity. It is a potential resource node in a future orbital economy. The implications extend to the history of the solar system itself. The existence of a population of co-orbital objects, suggests that the transport of material throughout the inner solar system is more efficient than previously thought. If 2025 PN7 is a captured main belt asteroid, it proves that the gravitational turnstiles of Jupiter and Mars are actively populating Earth's vicinity. If it is lunar ejecta, it proves that planets and moons exchange material regularly. This supports the concept of panspermia, the hypothesis that the chemical precursors to life, or even microbial life itself, could be transported between planetary bodies inside impact ejecta. While 2025 PN7 is likely sterile due to eons of exposure to harsh solar radiation and cosmic rays, the mechanism of its arrival in its current orbit validates the dynamical pathways required for such material transport. Let us delve deeper into the stability of the orbit, for this is where the mathematics of chaos theory intersects with astronomy. The 2080s limit is not a hard wall, but a statistical horizon. The motion of 2025 PN7 is governed by the n-body problem, which, for more than two bodies, has no general analytical solution. We can only approximate the position by iterating time steps. As we project further into the future, small uncertainties in the asteroid's current position and velocity amplify. This is the butterfly effect in orbital mechanics. The 2080s represents the point where the probability of the asteroid remaining in the horseshoe orbit drops significantly. It may transition into a tadpole orbit, oscillating around one of Earth's Lagrange points, or it may be ejected into a heliocentric orbit that no longer resonates with Earth. Observing 2025 PN7 over the next few years will allow astronomers to refine these measurements, shrinking the error bars and giving us a more precise date for its departure. The study of 2025 PN7 also forces us to re-evaluate our classification systems. The boundary between a moon and a quasi-moon is defined by gravity and perspective, but the boundary between an asteroid and a dormant comet is defined by composition. Is it possible that 2025 PN7 is a volatile-rich object? If it originated in the outer solar system, beyond the frost line, the distance from the sun where it is cold enough for volatile compounds like water, ammonia, and methane to condense into solid ice, it might contain pockets of ice deep beneath its crust. If it approaches the sun closer than usual during its orbital evolution, these ices could sublimate, turning directly from solid to gas, creating a weak, transient atmosphere or a tail. Observing such activity would be a profound discovery, blurring the lines between asteroid and comet and providing a fresh target for astrobiology. As we look toward the future, the what's next for 2025 PN7 involves a coordinated effort of ground-based and space-based astronomy. The upcoming generation of telescopes, such as the Vera C. Rubin Observatory in Chile, will be pivotal. With its massive wide-field camera, the Rubin Observatory will survey the entire visible southern sky every few nights. It will be able to track 2025 PN7 with unprecedented cadence, catching changes in its brightness that reveal its rotation rate and shape. Simultaneously, the James Webb Space Telescope, and by extension, its precise diameter. A dark, large object and a small, bright object can reflect the same amount of visible light, but they will emit vastly different amounts of heat. JWST can solve this degeneracy. The narrative of 2025 PN7 is also a narrative of data processing. The confirmation of this object wasn't a eureka moment where a scientist looked through an eyepiece and saw a rock. It was a victory of algorithms. The data streams from survey telescopes are vast, measuring in petabytes. Automated pipelines process this data, identifying transient sources. The discovery is often made by a piece of software flagging a probability, which is then verified by a human analyst. As we integrate artificial intelligence and machine learning into astronomy, our ability to find objects like 2025 PN7 will grow exponential. We may find that Earth has not just one or two quasi-moons, but a swarm of hundreds of tiny companions, a faint, invisible ring of debris sharing our journey around the Sun. This brings us to the philosophical and educational resonance of the event. 2025 PN7 reminds us that the solar system is not a finished product. It is still under construction. It is still evolving. The impacts, the captures, the orbital shifts, these are not things that happened only in the distant past. They are happening now. We are living in a dynamic environment. The presence of this quasi-moon challenges the static model of the solar system often taught in elementary schools. It introduces the public to the concepts of resonance, of relative reference frames, and of the impermanence of celestial arrangements. Furthermore, the limited time we have with 2025 PN7 until the 2080s serves as a reminder of the fleeting nature of observational opportunities. In the timescale of the universe, 50 years is less than a heartbeat. It is a single breath. Yet for humanity, it is a significant portion of a lifespan. It is a challenge to the current generation of astronomers and engineers to utilize this opportunity while it lasts. If we do not study 2025 PN7 now, if we do not launch missions to characterize it, the opportunity will pass. The rock will drift away into the darkness of the main solar system, becoming just another anonymous entry in the Minor Planet Center database, its secrets locked away perhaps forever. As we move toward the conclusion of this examination, let us summarize the journey of 2025 PN7. It began as an unknown, a faint statistical anomaly in a telescope's data stream. Through the rigorous application of orbital mechanics and astrometry, it was elevated to the status of a quasi-moon, a companion to Earth. It stands as a potential fragment of our own moon, returning to visit, or a wanderer from the asteroid belt captured by our gravity. It offers a unique destination for exploration, a testbed for planetary defense, and a resource for future industry. The story of 2025 PN7 is the story of our expanding vision. We are no longer confined to the surface of our planet, looking up in superstition. We are active observers, mapping our environment with mathematical precision. We are finding that the empty space around us is not empty at all. It is populated by these little travelers, these temporary moons that accompany us for a leg of our cosmic journey. In the decades to come, as Earth continues its revolutions around the Sun, 2025 PN7 will trace its horseshoe path, looping back and forth in the sky, a silent witness to human history. By the time it departs in the 2080s, humanity may look very different. We may have outposts on the Moon. We may have boot prints on Mars. When 2025 PN7 finally breaks its resonance and drifts away, it will leave behind a humanity that understands its place in the universe a little better than it did when the rock was discovered. The universe is a place of rhythms and cycles. Some cycles are short, like the day. Some are long, like the galactic year. The cycle of 2025 PN7 is a human-scale cycle. It is a visitor for our time. Its presence invites us to look up, to wonder, and to study. It reveals the intricate gravitational web that binds us to the solar system. It shows us that even in the vast emptiness of space, Earth is never truly alone. The dynamic space neighborhood continues to shift and turn, and as long as we keep watching, there will always be new companions to discover, new mysteries to solve, and new horizons to explore. This is the promise of astronomy, the endless frontier of knowledge, waiting to be charted, one asteroid at a time.